So next topic is, here we have 1,2 insertion and beta-hydride elimination. So these two are very important in examination point of view. Okay, so we just need to remember the conditions. First we'll go for 1,2 insertion. In 1,2 insertion, what will happens, the hydrogen which present on the metal that migrates from, this is the 1, okay, and this is 1 2. So 1 2 shift means the hydrogen which is present at the first position that migrates from 1 to 2. So now this hydrogen goes here and this carbon will come here. So now it will become like this, and there is a vacant site. Just remember this reaction. So based on this reaction we can write all the properties. The first one will go for the hapticity. So you see here the hapticity of olefin is N2 here, but here it converted into N1. So hapticity will change from N2 to N1. The second, here no vacant site, but here there is a vacant site on the metal. Third one, oxidation number. So this is the neutral ligand and this is also neutral. So there is no change in the oxidation state. No change in the oxidation state. So these are the three important properties we have to remember. So regarding this 1,2 insertion, and we will see one more reaction, CH2R. So here the vacant site is there. This reacts with olefin and this converts into like this. Now the hydrogen which is present here, 1,2 insertion means this is this 1 and this is 1 2. So now this CH2 comes here, this will become like this, and further this is also reacts with olefin, and further this reaction will continues like this. Now this will insert here, so further reaction will continue like this. So this is about the 1,2 insertion. So just you need to remember here only three things. The first one is hapticity. Hapticity is changing from the N2 to N1. Then there is a one vacant site is producing here and no change in the oxidation state. And we can see the coordination number also. Coordination number. So here coordination number is what is happening. By seeing this one we can say the coordination number is decreasing. So this is about the hapticity. Now we'll go for the eliminations. So there are three types of eliminations we have: alpha elimination, next beta hydride elimination, so this is alpha hydride elimination, okay, and third is delta hydride elimination. So first we will go for alpha elimination. Alpha elimination is nothing but CH2 Br. So if this is the leaving group and alpha to this means this will be alpha, so this hydrogen it takes and it produces simply alkenes. So this is a alpha elimination, alpha hydride elimination. So this is not that important, but this is very important. So beta hydride elimination is very important in examination point of view. So here also we'll first write the reaction. So based on that reaction we can predict all the properties. So the essential condition for beta hydride elimination is there should be one vacant site. So one vacant site is must. Okay, so this is the reaction for beta-hydride elimination. So here what is happening, so this is alpha and this is beta. So beta-hydride elimination, so the hydrogen will moving from the beta position onto the metal, so this is called beta-hydride elimination. And here this hydrogen is moving from here to onto metal, so because of that reason we are getting a double bond. So here the properties we can easily write. The first one is hapticity. So here we can make out the hapticity is here 1 and here is converting into 2, N1 to N2. Then what about oxidation number? So oxidation number will increase by 1 unit, because so we know that H is a negative ligand, right? So because of that reason H we can call it as a H minus, right? So here we have a H minus, so because of that reason the oxidation number will increase by 1 unit. Similarly coordination number increases by 1 unit. So here we can see only one coordination is there, here it's increased by 1 unit. Here we can see 2. Next, so next important point is this beta-hydride elimination is opposite to the 1,2 insertion. So if you see this way, this is 1,2 insertion. Okay, here also, so this is the 1,2 insertion. If you see this way, this is the beta-hydride elimination. See alpha, beta, the hydrogen which is present here, that is migrating from this carbon to onto the metal, so this is called beta-hydride elimination. Just remember, just opposite here in this two cases, on 2 insertion as well as beta-hydride eliminations, the properties are opposite. Here hapticity change from N2 to N1, here opposite, and then this coordination number decreased by 1 unit, but coordination number increased by 1 unit, and this is opposite to 1,2 insertion. And there are some conditions for beta-hydride elimination. Those conditions we'll see now. Conditions for beta-hydride elimination. So first one is there must be one vacant site. Must be one vacant site on the metal. The second one is must be one beta CH, means one beta hydrogen should be there. It should be one beta CH must be there. And all complexes which shows beta-hydride elimination, they are thermally unstable. So this we need to remember. So in the examination point of view, the questions mainly asked on these 3 properties. Okay, the first one is the metal should have one vacant site. This is the first condition. The second condition is metal should have one beta hydrogens. Beta hydrogens means this is alpha, beta, gamma. So here one hydrogen should be there. Then only this beta-hydride elimination will goes. Then they are thermally unstable. And the complexes where we have like this CH2, CH3, and here one vacant site is there. This is alpha and this is beta. So what's happening here, the beta hydrogen is present here, because of that this is thermally unstable. And where we have CH2, see this compound. So here this is alpha and this is beta. So here no beta hydrogen, no beta hydrogens. So because of that, in this case beta-hydride elimination is not possible. So due to that, this compound is stable compound, thermally stable. And then we have a compound like this, CH3, CH3, H. So here we have, this is alpha and this is beta, so we have one beta hydrogen, this is also unstable. Okay, and where we have a this kind of compounds, so this is alpha and this is beta, so this is also unstable, thermally unstable. So due to no beta hydrogen. Next one. So some complexes, what will happens, initially they will be 16 electron complexes and they can convert 18 electron complexes through this beta hydride eliminations. Like for example, we have rhodium, this one ppH3, and here one vacant site, the hydrogen, so this is alpha and this is beta, so just count it. So rhodium means ns2 nd7, that means 9 electrons plus this would be 5 plus this would be 2 plus 1, so total 16 electrons. So now this hydrogen goes from here to here and this will becomes RH, Cp, ppH3, hydrogen and wolfine, so this is converted into 18 electrons. Okay, and here this is thermally unstable, but this is stable because it's having a 18 electron complexes. So one more thing, if a 18 electron complex is there, so if that is having a beta hydrogens, so what about the stability, thermal stability? So if it undergoes, so imagine that 18 electron complex is there, in that we have a beta hydrogen. If undergoes beta hydride elimination, then it will become a 20 electron complex. So this is not possible because unstable complex can be converted into stable, but stable cannot convert into unstable, right? So even 18 electron complex is having beta hydrogens, that is thermally stable. This is very, very important. So even any 18 electron complex which is having beta hydrogens, that is thermally stable, so we can't say that is thermally unstable. So for example, we have a compound, this compound FeCO, this compound, and if we count number of electrons here, this is 4s2 3d6 8 electrons plus this is 5 plus this is 4 plus 1, so this is 18 electron complex. Okay, so now here in this case we have alpha as well as beta, so this also can undergoes beta hydride elimination, but if undergoes beta hydride elimination, it will convert into 20 electron species, so this is not possible. So just remember the complexes which are having 18 electron complexes, even they have beta hydrogens, they are thermally stable. And here we have 4 examples, 4 complexes: Pb CH3 4, second Pb ethyl 4, third titanium CH3 4, fourth titanium CH2 CH3 4. So the question is, which is thermally unstable? This is the question. Okay, so here no doubt this is not thermally unstable, so sorry, these two are stable because they don't have beta hydrogens. Only in these two cases we have a beta hydrogens, right? So here in this case we have Pb like this, and here also we have a titanium I think this is a tetrahedral shape. So one thing here we need to remember that in both the cases we have a beta hydrogens, but the main thing we need to remember, this beta hydride elimination is only for the transition metals, and this is not for the inner transition elements. Inner transition element is there means in that case we cannot expect any beta hydride eliminations. So in that case these two are stable, because here beta hydride elimination is not possible, and this is also stable, and the least stability will be this. Okay, if you see the stability order, so 1 will come more stable, then 2, then 3, and least stable will be 4. I think this is the correct order, because these two will not go. So beta hydride elimination, I think these are almost equal. I am not sure about these two. Okay, so next example we have 4 complexes: titanium, CH3 4, then titanium, CH2, PH4, titanium isopropyl group 4 times, titanium, CH3 4. So I asked increasing order of stability. Okay, so now we need to identify where beta hydride elimination is possible. So here it's not possible, and here also it's not possible, because this is like this: CH2, this is alpha, and this carbon is beta. The condition is there should be one beta hydrogen. If a hydrogen is there here, the aromaticity will be lost. So here no hydrogen is there, so because of that this will not undergo the beta hydride elimination. Next, here isopropyl group, here we have CH, CH3, and hydrogen here. So here we have a beta hydrogen, and ethyl group, though this also having the beta hydrogens. Okay, the least stability here is the more stable will be this one. Okay, so second will be more stable, and the next will goes to this one first, and the next will goes to ethyl group, and least stable will be 3. So this is the stability order. Okay, so these are the some questions on beta hydride eliminations. Next, we have alpha hydride eliminations. CH2H and H. Okay, so sorry, this is a vacant site. Now the hydrogen which is alpha to this can be alpha, so this is alpha. So this hydrogen migrates from here to here, and here we'll see the formation of a carbene. Sorry, this is not empty, this is also hydrogen. So sorry, so alpha hydride elimination means this hydrogen get eliminates, so because of that we will get a carbene. So just I had just made a mistake, so this is hydrogen only, not vacant site, and the alpha hydrogen, this is the alpha hydrogen which get eliminate, and it leads to forms the carbene. Okay, next, delta hydride elimination, it leads to form cyclic compounds. This is important. In this case there should be one vacant site and the hydrogen at delta position, alpha, beta, gamma, delta. This hydrogen goes from here to here and this forms a bond with metal. This hydrogen, alpha, beta, gamma, delta. So this is the compound here we'll get. So, and this is about the 1,2 insertion and beta-hydride eliminations. So I will be doing separately the previous questions on these topics. And if you like my video, please subscribe to my channel, and you can forward to your friends also. Thank you.